Okay, I decided to make this video because some of you did not have recitation classes on Wednesday. So let's start. I was planning to solve two problems in those recitation classes, and so let's cover them. First problem, 2347. So from chapter 23, problem 47. So what is about this problem? So we have a uniformly charged rod, flexible rod, right? So, and there's a charge Q uniformly distributed over this rod. And the length of the rod is L given. Right? So probably I should write immediately. We have total charge Q and the length L capital. Right? So then we take this rod, since it's flexible, we bend it into a semicircle. Right? And so now we have a semicircle. I will draw it here. Right. Semicircle. Yeah, total charge Q, length of that L, and so now we need to find electric field at the center of this circle. So let me put point P. So we need to find electric field created by this semicircle at the center. Right? So that's the problem. So let's start setting everything up. I will start first with probably introducing coordinate system. I will position here my y. This is x. And now I will write, so what we need to find electric field at point P. So that's what we need to find, right? So let's start. The beginning is standard because we're going to do integration, and the beginning is this. So far we have nothing in terms of expressions to find electric field except for the expression to find electric field created by a point charge. Right? We know that. Electric field created by a point charge, for example at this point, so E equals K times Q, and divided by the square of the distance from the charge to the point where you want to find electric field. So that's it, nothing else. So we have to use that somehow to solve this problem. And the beginning is this. So let's take an infinitesimally small piece of this rod. I will take it over here. Right. So that's my infinitesimally small section of this rod of length dl. So, and I will write, take an infinitesimally small dl. And of course, this small section will have a small amount of charge dq. Right? Okay, now, what does it mean infinitesimally small? From the calculus point of view, infinitesimally small, it is smaller than anything you can think of. If you think this is small, this is smaller, dl is smaller. If you think that is small, dl is small. It doesn't matter how creative you in terms of imagining this small dl, this dl will be smaller. Right? So if it's so small, it means that we can treat this dl as a point charge. Of course, with this amount of charge dq. Probably I should write it here, dq. So we can treat this dl with charge dq as the point charge. So we'll take this infinitesimal small dl and treat it as a point charge. It's very important statement at the beginning. Right? Okay, and we know now we know the expression for the electric field. So let me first draw that electric field. So contribution from this charge, point charge dq, to the electric field at point P, I can draw it with this vector. So this will be my dE, right? And magnitude of this dE I can now easily write because it's a point charge. So I can write that dE equals k. So usually it's a k times q divided by square of the distance, but our charge is dq. So I can write k dq divided by r squared. Okay, so that's the beginning. So next step, we need to write, before we start integrating them, we need to write all these pieces, right, dq, r, in terms of what is given and what is given, q and l. And in terms of a variable of integration. Which variable of integration we are going to use from the very beginning, very often it's difficult to tell. But we'll see which variable of integration we will end up with. Okay, anyway, so let's start first with writing what is r. R on the picture, it's this distance from the point charge to the point in question. So this is r small, which is equal to radius of this circle. Okay, radius is not given. This length is given, but later on at a certain point, we'll make a transition from r to l. So for now, let's use this r capital. So, and this r small, it's this distance, it's a constant r capital, right? Because this is the center of the circle. Now, dq. Of course, that's the amount of charge in this small section. This is, we have in this object, we have a linear charge distribution. We have linear charge distribution. So let's for a minute assume that we know this linear charge distribution. To refresh those charge densities, because now we need to use charge densities. You can look at my view graphs a couple of lectures ago. So it's a linear charge distribution. So let's assume that I know linear charge density, lambda, linear charge density. It's amount of charge per unit length. So in order to find dq, we need to take this lambda and multiply it by the length of this section. So lambda times dl. Okay. But of course, lambda right now is not given, so we need to find lambda. Okay, but it's very simple. Since we have charge distributed uniformly, so we just need to take the total charge and divide it by the total length of the rod. Again, we discussed it a couple of lectures ago. So linear charge density I can write as the total charge divided by the total length, right? So linear charge density. So that's my explanation box. I'm just explaining what I'm doing when I move from this point to the next point. Right? So I can now plug, instead of lambda, it will be q dl over L capital. So now, for now it looks like we have a variable of integration L. But I know the solution, and I know that this variable of integration is not the best. So what we're going to do, let's switch from this variable of integration L to a different, to an angle. Which angle I'm talking about? I'm planning to use this angle. You know what, I will probably use red because it's important. Right, this angle theta. It's an angle from positive y direction in counterclockwise direction to dl. Right. Okay, then let's also draw on the picture d theta. It's an angle subtended by this arc length dl. Okay, and that will be my d theta. D theta. Okay, now let's try to make a transition. In physics 1, we introduce radians. So angle can be measured in terms of degrees. We can also use radians to measure angles. Let's refresh that, because usually students by this time they forget about definition of radians. So let me refresh this. So let's assume that you have a circle, right, of radius r. Right, so radius r. And let's take this, for example, arc length. It's not infinitesimally small. For now, it's just a arc length L. And of course, this is angle theta, right, subtended by this arc length L. So, by definition, in physics 1, we defined angle theta in radians. I will put 3 lines. By definition, it's a ratio of this arc length L and the radius, and this radius r. So it will be L over r. So that's the definition of angle in radians. Right? Okay, so now let me rewrite it in this way. L equals r theta. Right? I just rewrote in a slightly different way. And now let's write differential form of this expression. So since r is constant, right, as we move around the circle, r stays the same, right? So it should be, so I can write dl equals r d theta, and that's what I want. So I can write dl equals r d theta. Okay, let me separate it because that's sort of small digression from what we've been doing. So that's what I wanted to use in order to make a transition from L to theta. So dl equals r d theta. So I'm going to use it over here, right? Let me put this small arrow. So that's what I'm going to use to change a variable of integration. Okay, so as a result, I can write it will be q r d theta divided by L. So that's my amount of charge, right? Written in terms of given. Okay, actually r is not given, but in a few minutes we will replace it and write it in terms of L. Just now I don't want to make that replacement. So QRL is given and variable of integration theta. Okay, so it looks like we are all set in order to put all these r and this dq into our expression. Right. So as a result, I can write dE equals k q r d theta divided by L and r squared. So this r squared comes from this r, and the rest is q r d theta L. Q r d theta L, and of course constant in front. Right. Okay, so now what happens with one of these r? Of course, one of these r can be cancelled, and what will be left? K q d theta divided by L times r. And now, in my opinion, it's time to get rid of r and write it in terms of L, because again, r is not given, L is given. The total length of the rod, the total length is of this semicircle, because we bent that rod, you remember. Okay, so again, I will open my explanation box to show how I going to get rid of this r. So what we know the total length of the rod, L, and at the same time, okay, this is the semicircle. We know the circumference of this semicircle. It's a pi r. The circumference of circle, 2 pi r. But since we have only half of the circle, so it's a pi r. So L equals to pi r. So I can write total length L equals to pi times r. And I will close my explanation box. You know what? I will write L r equals L divided by pi. Okay, so that's what I'm going to use here r equals L over pi. And let me continue over here. So dE will be equal k q d theta L, and instead of r now I can write L over pi, L divided by pi. Okay, so this pi will go upstairs in the numerator, and downstairs we'll have L to the power of 2. So it will be k pi q d theta divided by L squared. Okay, so that's magnitude. Again, it's a magnitude of this vector. It's a contribution to the net electric field at this point P from this small section dl with the charge dq, right? It's only contribution, small contribution to the net electric field at point P. Okay, so next, and again, everything is written in terms of what is given and the variable of integration. Q is given, L is given, variable of integration, I decided to use theta. So next, of course, we're supposed to start integrating it. First, of course, you're supposed to find a y component of this electric field and integrate it. Then find x component, because this is the vector. Then find x component of this electric field, and again integrate over the whole semicircle. But let's try to use symmetry and simplify the amount, or not, reduce the amount of integration. So let me, because obviously there is a plenty of symmetry. If you look from this point, from the point P, where we want to find the electric field on the object, right, there are plenty of symmetry. So maybe it will help. So let me write by symmetry. So what we get, what can we get out of this symmetry? Okay, I will use probably a different color. Look, we have this segment in the upper part of this semicircle, but at the same time we can find a similar segment with the same length dl, right, and the same amount of charge dq in the lower part of this semicircle, right? Just straight down. And of course this segment with the charge dq will create its own contribution to the electric field at point P. And that contribution, let me draw it over here, right? The blue marker, right? So this will be dE, right? And now let's decompose this blue vector and red vector into along the x and y directions. Let me do first with the blue one. So this will be x component. This will be y component, right? And now the same with the red one. Red give us this x component, and the y component will be here, right? And now let's look carefully. What happens with the y components? This blue component and this red component, y components, they just cancel each other. Let me just cross them with a small cross, okay? All right. So they just cancel each other. And for any section over here, we can find a symmetrically positioned section in the lower part of the semicircle, and the y components will be canceling each other every time. So as a result, I can say that y component of the net electric field must be 0. Of course, if you find the y component and do integration as it's supposed to be done from the mathematical point of view, you will end up with 0 anyway. Most likely you're going to have odd function, integration of an odd function over symmetrical limits. Okay, so I can write by symmetry, electric y component of the net electric field at point P will be 0. That's one piece of an answer. So let me frame it, and of course later I will rewrite it. So I don't have to do integration over y component. So now we have to take care only of the x component. So let's find x component and integrate it. So, in order to find x component, I need one of these angles. Since I introduce angle theta, you see, exactly the same angle is over here, theta, because this, you see, this angle and that angle, they're equal because they are vertical, right? So, we know this angle, so as a result, it also over here, this angle is also by geometry theta. So if you want to find this x component of this electric field, so you need to take dE and multiply by sine of this angle, because we want to find the side which is opposite to the angle. Opposite side in the right triangle, of course, you're supposed to use sine function. So let me write it down. Probably I will write just underneath, start writing dEx. So it will be, of course, dE times sine of angle theta. Right? Okay, and now, yeah, probably I will plug dE, and then I will start talking about the integration. Right? So now I can plug this. This is dE. I will put it here. K pi q d theta L squared and times sine of theta. Okay, so that's expression which we're supposed to integrate. I will write underneath E sub x equals integral of dEx integral, and I will just rewrite it. K pi q, I will write sine first, sine theta d theta, and divided by L squared. Now we need to write down limits of integration, lower limit and upper limit. We start integrating from the top. And when you are at the top, when you infinitesimally small segment over here, angle theta is 0, right? You see, we measure angle theta from the vertical direction. So when you are here, of course, angle is 0. So it means that the lower limit is 0. Now, upper limit, so you start integrating, you'll take this segment, then next one, next one, next one, and when you get all the way to the bottom, to this point, your angle will be pi. You see, here it's 0, but when you walk around and you get to this part of the semicircle, your angle is pi. So it's from 0 to pi. Okay, now let's try to understand what can be done with this integral. K is constant, so we can take it outside of the integral. Pi also constant, q also given some constant number, L squared also constant. So this whole thing is constant, and it can be taken outside of this integral because it's a constant. Right, and so what's left will be integral of sine theta d theta. So let me rewrite it. K pi q over L squared, integral from 0 to pi, sine theta d theta. And of course, this is a trivial integral. Integral of sine theta d theta is just minus cosine theta. So it will be k pi q over L squared minus cosine theta, and with limits from 0 to pi. Okay, and the last line probably. I will take minus outside. It will be minus k pi q over L squared. And now first, of course, you need to evaluate cosine at the upper limit. So it's a cosine of pi minus 1. Minus 1. Then minus the value of this function at the lower limit. Minus cosine at 0 is 1. So it's again minus 1. So we have minus 2, and here minus in front. So it will be just 2 times this factor. It will be 2k pi q over L squared. So that's the x component of the net electric field at point P, and the y component is 0. So let me write over here sort of the answer. E sub x equals 2k pi q over L squared, and E sub y equals 0. Let me frame it. That's the answer. Okay, this problem will be very useful when you start solving one of problems in your homework. But of course, I think instead of semicircle, you will have a quarter of a circle. I don't remember exactly, right? So, and again, don't forget about this trick, how to make a transition from dl to d theta. You have to remember definition of angle in radians, how to measure angle in radians.